In this video, we'll be dealing with the following scenario. The capacitor is charged to 50 volts. The switch closes at t equals 0 seconds. Draw a graph showing the magnetic field strength as a function of time at the position of the dot. On your graph, indicate the maximum field strength and provide an appropriate numerical scale on the horizontal axis. So the problem statement suggests that the capacitor starts out fully charged, and once the switch is closed, the charge will move away from the capacitor and discharge the capacitor. And so we'll start out with the equation for a discharging capacitor, which is Q as a function of time equals Q naught times e to the negative t over RC. And we know that just a plain old charge gives rise to electric fields, but we're interested in the magnetic field, and moving charge or current gives rise to magnetic fields. And so we'll use the relationship current equals change in charge over change in time to yield an equation that we'll be able to use for this problem. And since current and charge are directly proportional, we'll just replace Q in this equation with I, and that'll give us I equals I max times e to the negative t over RC. And we know that this will be I max because since it's discharging, the value at t equals 0 will be the biggest. And then we'll use Ohm's law to get current equals V over R, or voltage over resistance, and that'll give us the equation V over R times e to the negative t over RC. And here I plugged in values that were given in the problem statement, and that is 50 volts over 5 ohms times e to the negative t over 1 times 10 to the negative 5 seconds. And I got this value from solving RC, which is resistance times capacitance, which was 5 ohms times 2 times 10 to the negative 6 farads, which was the conversion of 2 microfarads to farads, and that'll yield 1 times 10 to the negative 5 seconds. And that gave us 10 amps times e to the negative t over 1 times 10 to the negative 5 seconds for current. And for a magnetic field, we'll be using the equation for magnetic field given off by a wire, because the magnetic field strength felt at this point will be given off from this wire of the circuit. And so that'll give us mu naught over 2 pi d times what we found for current earlier, which was 10 amps times e to the negative t over 1 times 10 to the negative 5 seconds. And now plugging in known values, mu naught is 4 pi times 10 to the negative 7th over 2 pi, and distance is 1 times 10 to the negative 2 meters, which was the 1 centimeter converted to meters, and this is I that we found earlier, and that'll yield our general equation for the graph that we'll be generating, and it's 2 times 10 to the negative 4 Tesla times e to the negative t over 1 times 10 to the negative 5 seconds. And to find I max, we plug in to find the maximum magnetic field strength, we plug in t equals 0, and that'll give us e to the 0 over 1 times 10 to the negative 5 seconds, which will be just e to the 0, which is 1, and so that'll yield 2 times 10 to the negative 4 Tesla. And here is the graph that I've generated. Here is the maximum magnetic field strength, 2 times 10 to the negative 4 Tesla. And I've generated this curve by plugging in various other times for t in our general equation, and that'll give this graph. And I've converted the time back to microseconds for the scale, just for a neater graph. And here is the end result.